solve all the questions I've given you, that question you're trying. Once we are done with it, we can now call it a day for physics. So please, I will start with permittivity. From the word permission, you get permittivity. So permittivity talks about the ease of movement of charges in an electric field. I said it is the ease. Permittivity talks about how easy it is for charges to move in an electric field. In some textbooks, you see it as how easy it is for electric field lines to move. But the main thing is this one I'm saying. I said the ease of movement of charges in an electric field. That is what permittivity is. So sometimes you see your textbook movement of electric field lines. Electric field lines is simply imaginary line that you are using to show how charge is moving. So the main thing there is the charge. So if I know that, listen to this, that permittivity, we have the one we call permittivity of free space represented with inverse. This permittivity of free space is constant. You see that I can put this time, then we have what we call, I say this region whereby electric force is experienced by a test charge. You can say it this way, put it this way, better this way. Electric field is a region created by a source charge. Electric field is a region created by a source charge. Electric field is a region created by a source charge where electric force or electric field effects is experienced by a test charge. Where electric force or electric field effects is experienced by a test charge. There are so many ways to define electric field, but this one I'm telling you so you understand what really happens here. So I said it's a region created by a source charge where electric force or electric field effects is experienced by a test charge. So you know that now. So one creates it, the bigger charge creates it. One, definitely, when it was created that just is more like this, I have a charge now. Because this thing is charged, positive or negative, automatically it builds up a region around it because it has that ability that there's something like positive or negative inside it. It creates something around it. So for the fact that there's no charge coming here, the field is just there. But the minute there's another charge coming to this, if that charge is outside, maybe a smaller charge, if that charge is outside, it can't feel the effect here. It has its own field. But the minute they are now, this one now come here, because this one is bigger. I told you in the last class, source charge is always bigger. Immediately, this one will either, if this is opposite charge, immediately because it will either attract it, and if it's the same charge, it will repel it. So you need to know that. So that is the first thing you are knowing about electric field, but that is not all. I want to claim. You need to know that this electric field don't just, so I'm supposed to put electric field there to the electric field line. I cannot talk about electric field without talking about electric field line. So this electric field, we know it's that charge creates it. But for us to be able to show what is happening, we must use an imaginary line. I said electric field line is an imaginary line that shows the direction of electric field, or you say the direction of charges in an electric field. Electric field line is an imaginary line that shows the direction of charges in an electric field. So if you know that, the minute I have, let's say, a surface, let's say I have a surface. Let's say I have a surface. This surface that I have like this is lying down. I can also have this surface when it's like this, depending on how it is placed. I said electric field line is an imaginary line that is used to show the direction of charges in an electric field. So let's say I have this. Charges can be on this surface. We remember that in our last class we said that whenever a body is heated up or is charged, charge is inside it rush to the surface. We said it in our first class. Always have it in mind. And if it rushes to the surface, as it gets to the surface, the next thing it will be checking is for the sharpest points, like the edges, where it is the sharpest. That is what we call action of point phenomenon. So if I know that, for example, if I'm having like, let's say, one charge here, one charge here, one charge here, one charge here, you see that at this sharpest point you have many charges. Because it's trying to escape, but it can't escape. So that sharpest point, smallest point looks like something that can let it out as it's going around. So on the surface, it will always gather at the surface, but it will then have more at the sharpest points. You need to note that. That is what you call action of point phenomenon. And that action of point phenomenon creates what we call coronal discharge. Coronal discharge is simply the air around that region will get ionized. So I'm just using this thing, it's not must, it's many like this. But I'm just using it to illustrate. So this charge now has gathered. The next thing you need to ask yourself, because I want you to see the direction here now. for the fact that this surface is this way, is lying down, is like lying down, how do you think the normal force will be acting? The normal force on this object will be acting upwards. Is it not true? Gravitation acts downward. Now normal force will be like going up. So let's say that there's N for normal. Normal force always acts 90 degrees. Remember. So if I know that, let's say now that I'm not taking it that charge is coming from anywhere and hitting this thing. I'm not taking it that charge is coming from anywhere and hitting this thing. Let's say that I now know that this particular positive charge that I have here, this particular positive charge that I have here, is having its electric field direction going this way. Do you know why I'm putting it this way? Because there is a rule I want to point out with this thing I'm saying, that electric field lines always move 90 degrees to the normal. I did not say to the plane surface. So I said to the normal. Notice that the normal here is this way because this surface is lying down. Assuming this surface is standing like this. Assuming this surface is standing like this, it's standing like this. Notice that we are going to be considering when it's a plane surface, the normal now, even though that is at an angle, to be 90 degrees to this. So if I want to ask you how the electric field be acting, yes, now notice that it is slanted. It's not like I did not put it this way. Assuming I put it this way, I will say, okay, consider it that the normal now, 90 degrees will be facing this way. So I want to use this so that you see it's 90 degrees. Now the electric field, automatically the line should be going this way. Let's say this is normal. This is the E. Because we will still come across this in electric flux. So it's important to note it here when we start doing electric flux. So notice the rule I'm trying to give is that the field line, the direction of the field line, always points 90 degrees to the normal. That's the point I'm trying to make. It's not 90 degrees to the plane surface. What you first of all be checking is where is the normal? How is the surface? Is it lying down? If it's horizontal, if the surface is horizontal, the normal will be going up. And if, let's say, like for a ceiling now that is already hanging, whatever charge that is on it should be pointing down. So it's 90 degrees coming down. And if that surface happens to be standing vertically, that means the normal should be going this way. And if it's standing this way, then towards this side, the normal should be coming this way. So in that case, you always check it that if the normal is going this way, the electric field should be this way. And if the normal is this way, the electric field should be this way or this way. But there are cases where you can have geometry, that is two openings. We will get to that in Gauss surface. So let's leave it aside. So it's not only one direction that electric field flow. It can flow both ways at the same time, or up and down at the same time. It depends on the surface. If the surface has just one opening, the charge is just on one surface, it will not be one. But if it's on both surfaces, up and down, depending on the geometry of that material, it can come up, it can come down, it can go left, it can go right. So just don't think about that one. We get to it at Gaussian surface, but just note this rule that I'm trying to show you now. This rule that everything electric field flows once it's going through a surface, in summer, once it's going through a surface, it flows 90 degrees to the normal. But it does not mean that every time electric field should be acting, should be going through a surface. There are cases where I can have, let's say this is a surface now. Let's say I have this to be a surface. And the charges are not coming to this surface. Let's say we just have our electric field flowing this way. Physicists are sure this is more like an assumption because it can happen. A situation whereby the electric field is not going through the surface, it is along. It is along, not through the surface and not on the surface. In that case, we take it that if, for example, this thing now is the normal, for this thing to be flat, if this is the normal, and you can see that if you take this thing up now, watch, if you decide to take this thing up to cut across this, you can now see that this normal, this 90 degrees here, has nothing to do with this electric field. Are you getting it? In this case, we consider the flux here to be parallel. parallel in the sense that this thing that you see here is also here, that is going on its own. That is, if you are remembering our physics of equilibrium, if something is here, so it has nothing to do with cutting inside here. Somebody will want to say, what if it passed through here? Remember, it's more like an assumption. We are saying a situation where it did not pass through that surface, but around that region, we know that there is a field, but it has nothing to do with this plane surface, just through it. So in that case, there is no angle, there is no business with that. Is it confusing? Yes. Hey. Do you understand this one? Yes. That if we have, let's say, a surface this way, and we say that the charge is on this surface, like the way we place this one, that the surface is like standing, that we are considering the normal to be this way. And if it's this way, we are considering the normal to be this way. We are not looking at the plane surface. We are looking at the force effect, like acting, or should I say, 90 degrees to that surface. So that is what I did. I now said that whenever you get the normal, go and check the electric field. Put it at 90 degrees. That is where we are. For through the surface, let's leave it till we get to electric flux. I have something to say before that so that it will make more sense. So first thing first, you know what electric field is now. It is always created by a charge. Then a test charge experiences it. Then second, you know that you use field lines to show electric field. Which means that if, for example, I have positive charge, negative charge, watch, I am trying to pretend as if I have not come to this thing now, since it's confusing, so that I will relax and get electric field intensity, make you understand it. Then when I get to flux, you must understand it now. Now see, if this is for electric field line, I have positive and negative. We are saying that there is a rule that you must obey, and that rule is simply that I cannot have, for example, this thing like this, Electric field line does not intersect. First rule, the very important first rule, it does not intersect. So if I have positive and negative, I know that naturally, another rule, naturally, positive charges move outwards. Should they have told you before? Why negative charges move inwards? So that is the second. Positive charge move outwards, negative move inwards. You will see sometimes in your textbook they draw positive like this, draw positive like this, draw positive like this. In your mind, you want to be using this thing. This thing is just as an illustration. You don't draw two charges with straight line. Every charge intersecting or repelling must be shown by a spherical curve. So it must move as a curve. So I just hope you are noting all the rules. First one, they don't intersect. Secondly, charges point outward from the positive charge and inward from the negative charge. So if I'm drawing this, depending on how you want to draw yours, just get the point. That's the main thing I want you to get. Then know how we solve the question. Then, however question comes, you are able to interpret it. How many things you put here matters. If I put, let's say, 2 here, and I put 1 here, I am now confusing it. I'm now saying that there is more charge here than this one. Can you hear me? So the number of arrows you put should be equal, the same way. Else, what you are suggesting is that one is having more charge than the other. So, and notice, at the end of the day, I can come somewhere here to show that this thing is pointing. Notice I put 3 here. Okay, it's supposed to be like 4. And you don't have an imbalance like this one I'm doing. So, let's say I have another charge here. So this thing is just to show that it's pointing inwards. So I can now make things balance up. I can put more here. I'm being fast. That's why I'm not drawing it the way you want to see it. Pardon. Because I want us to solve questions, because it's not just explanation that makes us understand it. So it must be a curve. That's the point I'm trying to make. Sorry, wait. Thank you. So remember, positive charge is point outward, Shabin? Then a question on this can be in electricity. In electricity, an objective question. In electricity, charges move from higher potential to lower potential, or lower potential to higher potential. Charges move in electricity. It is believed that charges move from higher potential to lower potential, or lower potential to higher potential. Lower to higher. Somebody say lower to higher. If it's electron, to lower to higher. That's not what I'm asking. I said charges. So please, the answer for charges is simply higher potential to lower potential. Do you know why? It is believed in physics that charges that we are talking about is positive charge. That is why you see in some textbooks they will tell you the movement of positive charge or positive Q charge, that is the belief. So charges, what I'm trying to say with that is that charges originate or start from the positive terminal and then end at the negative terminal. So you need to know that. So whenever somebody tells you charges, that person is automatically just telling you positive charge. But if that person wants you to know that it's electron, the person will specify negative charge. So negative charge moves from lower potential, because notice now this is the lower potential they are talking about. Is it not true? So if there's any work that has to do with potential means normally this electron moves practically, but in physics they believe it's the positive that is moving. But the minute you talk about potential, they are saying is work done. So if work is done moving something from positive, for it to return, there is also work for it to return to the positive again. So that work done from lower potential to higher potential is talking about electron. So the charge there is electron. So normally in physics, or less specified, charges move from higher potential to lower potential. But if specified, lower to higher, you know that they are talking about electron, they must tell you. So if I know that, I want to believe that somehow this one is simple, electric field line is simple. Let's not waste time here. So let's move to electric field intensity. Another name for this electric field intensity is electric field strength. Why I'm rushing this a bit is that it's not like they believe you will have the knowledge, it will be there. Nobody is coming inside the exam to tell you, define electric field strength, but they believe the knowledge you have it. So electric field strength, I want to claim. Or you call it electric field intensity. In physics, when you are solving calculation question, you take it that you don't know the formula for electric field though. But whatever formula you have for electric field strength, that is electric field. That is the formula used for electric field. When they ask you to calculate the electric field, there are so many cases we will come across. So, in summary, if you know that there is something like electric field, they are now coming to put electric field strength to it. It is simply talking about how much of electric field you have. So how strong or weak that your electric field is, that is what electric field intensity is all about. I know that you've read where they said it is force per unit charge. You've heard that before. But it is simply talking about how strong. If you remember, I told you in first semester that if I have, for example, mass, density, equals to mass over volume. This density is talking about you must have a volume. You must have a volume before you have those masses. Is it not true? And I told you that density talks about how heavy or light something is. If I bring like foam, I put inside 50 kg, bring stone, put inside 50 kg, the stone will be heavier. Is it not true? That means it's denser. So there must be the main thing. Anytime you have a situation where you have numerator and denominator, the main thing here is volume. Without the volume, we can't check this mass inside to know if it's deep or not. So for that same case, where you come and see that electric field intensity is force over charge. Without the charge, you cannot know how much force is being applied to this charge. Are you getting the point now? So that is simply that electric field intensity is just talking about how much charge you have in an electric field. And you know that when you have charge in an electric field, you've created, how much charge or how much force, you have. The best way to put it is, how much force is acting on a charge in an electric field? Electric field intensity. How much force is acting on a charge in an electric field? Remember, charge creates electric field. So how much force acting there? That is what you know as electric field intensity. So it's simply how weak or strong your electric field is. That is electric field intensity. So they are the same thing. They are the same thing. So sometimes they quote it as force per unit charge. In the same thing. So I said, how much force is acting on a charge in the electric field or in an electric field? That's what electric field intensity is. So please, I want to claim this. Look at this. Look at this. Look at this. Normally, first semester we said that force is equals to MA, Shemi. If force is equals to MA, you remember I once told you that charge is simply the same thing as mass. Just that when it has to do with gravitation, you are looking at mass, that force field. If it's gravitational field, is mass. If it's electric field, is now charge. So I said that the internal, you can see so many definitions, but the internal, internal ability a body has, or you say the internal property, or you say the internal feature that a property or a matter has that makes it attractive or repulsive is known as charge. If you don't want to define it that way, you define it the same way you define mass. The amount of matter, but instead of just amount of matter, it's not amount of attractive or repulsive matter. And instead of saying in a body, you say in an electric field. Are you getting it now? So if I know that, the same thing with force, just come and replace this M with Q equals to F. Now see, for A here that is acceleration, when it has to do with electric field, force there, the A here is simply going to be represented with electric field intensity. Can you see it? Yes. Remember what acceleration talks about? Change in velocity. So the change that will happen to this charge, whatever is happening to this body, how it's moving and whatever, is determined by this. How much of what we have here is determined by this. So when you make this order of the formula, you're now having E equals to F over Q. Thank you. So please, that is how you got this. Always note it. And these two formulas, you can put it interchangeably as well. You can also have, since this is this thing, you can say MA is also equals to QE. This thing is also valid. This is also valid. Note that. This is also valid. If you don't have F equals to MA, you can just say MA equals to QE. Since F is equals to MA, you can put this as well. So now that you know this for electric field intensity or strength, remember I said it has to do with how much of electric field, how much the electric field is. If it's strong, if it's weak, the force acting on your electric field, the charge in your electric field, that's the electric field strength. Let's move to flux now, because this flux code will take me back to that thing that we when we started. So, electric flux, I want to claim. So I think the best way to put this in, before electric field potential, I should have Gauss theory before electric field potential, because they are more related than electric potential. Somebody said Chile. Don't worry, just right. You know, this thing is because we are just starting. Once we progress now deep into the semester, all these ones now will look like normal thing. So see something. So electric flux, right? Electric flux. I hope my sharp. Electric flux. So I will represent electric flux using this. I want you to get this because question is what we are supposed to solve. But me taking time to do this is because I want you to learn it, like know it, normal. It's just like when somebody tells you what is vector, you say it has magnitude, direction, scan ahead. This is the basics like that thing in second semester. So when you hear electric field flux or electric flux, it's just talking about electric field flux. It's just talking about how much of electric field intensity you have. Can you hear me? When you hear electric field flux, it is simply talking about how much or how many electric field strengths do you have. You know that electric field strength talks about how strong your charge is or how weak. Now, for electric flux, it's simply saying how many electric field strengths do you have. I'll still define it, I'm just explaining. So how many of electric field intensity do you have in that electric field? Is it confusing? So we define electric field flux as the collection of electric field intensity. We say it is the collection, or you say the sum total of electric field strengths in a given area, or you say in a given area of electric field. I said electric flux is the collection, or you say the sum total is the collection, or you say the sum total of electric field strengths. The sum total, or you say the collection of electric field intensity, the collection, how much of it, I'm looking for another way to put it. If I know that electric field intensity talks about force per unit charge, electric field flux is simply saying the electric field you have on an area, how strong it is, and how many of it do you have in that particular surface. Is it confusing? I said electric field flux is saying we already know electric field intensity, Shebi. Now, electric field flux is simply saying the electric field intensity that you have, which I said you also take as electric field because it's the same. It's just that electric field intensity describes electric field. That's what electric field intensity is doing. It's describing the electric field. It's telling you what is happening there. So I'm not saying that electric field flux is simply saying how much of electric field intensity is in a given area, or is in a given surface, or is in a given volume. That's what electric flux is. How much of it is in a given area? Remember that electric field intensity is just describing a field that has been created. Is it strong? Is it not strong? But electric flux is now bringing it to a surface, or to a volume, or to a line. That is why we normally say that electric field flux describes more of the density of electric field more than the intensity. We say that electric field flux describes or talks about the depth of electric field more than it does with the intensity. So if I know that we give this, don't worry, we give this as EA, that is electric field intensity, so you say electric field times area. Electric field times area. I know why I lifted this thing from theory, because these two are very related. They are very related. Now, do you know that this particular formula I am seeing here, is also the same thing as something I'm going to show you. Just notice that once they ask you for electric field flux, what they are asking you is how much electric field is in a given surface, or how much electric field is in a given volume, or how much electric field is in a given line of charge. While if it's electric field intensity, they are asking you how much force is acting on a charge. So you get the two now. Now see, this E that I'm seeing here, if you remember, from what we've done so far, we said somewhere where we said MA is equals to QE. Is it true? Then there's somewhere we said also that F is equals to MA. But if you remember Coulomb's law, is F is equals to KQ squared over R squared, should be? Now, I don't want to use K, Q square. I want to use Q and Q naught. Anybody that understands physics well, immediately you see this Q and Q naught. As a student of physics, you take the first one to mean source charge, the second one to mean test charge. Always. The one that creates the field, the one that experiences the field. Now, if I put this thing here, I can replace this. Let's say I put this thing back. I can replace this. That is equal force here. So I can now have KQ and then Q naught equals to QE. But there's something, see? Over R square. Thank you. Look at this thing. Look at this thing. Here that I have F equals to QE. Notice that this thing is electric field. Is it not true? And we said that, when we started, we said that electric field intensity talks about amount of force that is acting on a charge. Is it not true? Is it what we said? Yes. That means that whenever we are talking about electric field intensity, the first idea is that the charge here is not really the source charge, but the test charge. There has to be a charge. Then force will be acting on it. Is it not true? Watch. We said that there will be a charge for force to act on. If there is a charge that force is acting on, what of the charge, the charge that created that field? That one is the source now. The one force is acting on is this one. So that means this is supposed to have this. It's important to know these things like this, because when questions are asked, it is what will help you mix things well to know what you are solving. So that means this Q here is a test charge. So if I know that this should be this way, I can cancel this, cancel this. That means that another formula for electric field intensity is E equals to KQ over R squared. So whenever a question is given to you, as we progress, you will see, and that question talks about electric field that has charge creating it, that has created it for a source charge. This is the formula to use if you have source charge without stressing yourself. But if, for example, you are now having a situation whereby you have a test charge, to stress yourself, without stressing yourself, sorry, this is the formula you're supposed to use for electric field intensity. So this is when there is test charge. This is when there is source charge. It might be looking plenty, but it's not plenty. Just be noting it. Noting it. It's not plenty. Because force is acting on something, or something is experiencing, is test. The one that creates is source. So these two formulas, but if it will confuse you, just write it. No stress. As we start solving questions, you will understand. Now, what I want to do is to say, for the fact that I have this thing, and I have this thing, it simply means that I, that is naught, which is electric flux, can be the same thing as F over Q naught A. It can be the same thing as F over Q naught A. But in physics, we hardly think about this, we hardly make use of this. So this can also be the same thing as saying I naught electric flux is equals to KQ over R squared A. This is the one we make use of for Gauss theory. And you will see how it relates us to Gauss theory. It takes us to Gauss theory. Can I clean this? Be fast, be fast, be fast. What we are getting is the foundation. This period, what you are doing is like that time you started first semester, that I was teaching you vectors, measurements. It's just the same thing we are doing. You will see that as we move with time, this one will look like small thing to you. So this is the foundation, and it's important to master it. So I can clean. Now see, you now see that if this A is here, this A can mean many things. You now need to know that there's something we call charge distribution. This A here means area, is it not true? Yes. So when we are talking about electric flux, we always say electric field. Is it on a surface? If it's on a surface, is the surface cylindrical? Is the surface a sphere? These are the things you will now be asking. So if the surface is a sphere, what we just need to do is to find the area of a sphere. If the surface is a cylinder, what we need to do is to find the area of a cylinder. Instead of A here, we replace it with area of a cylinder. Instead of A here, if it's a sphere, we replace it with area of a sphere. So what I can do here is to come for sphere. I'll have this to be the same thing as saying KQ over R squared. Area of a sphere is what?
4 pi r.
Is it true?
Yes.
Check for me, I'll be sure.
Yes.
Now see, using this 4 pi r squared for sphere, that is what Gauss used to get another principle that I will give you for this electric flux. This thing can cancel this thing. Do you agree? Do you agree?
Yes.
So that an electric flux will be equal to what? KQ 4 pi shading.
Yes.
But do you remember somewhere in your book, when we started, I told you that K is a constant that is equal to 1 over 4 pi. Eh? 4 what? 4 over 3. Is it not volume we are talking about? It's area we are talking about now. When you differentiate volume, I think you will get area. When you integrate area, you get volume. So just whatever volume you have, differentiate it, you get what we have. And I always want you to use that because when you come to cylinder, you notice that cylinder, the volume of cylinder is just pi r squared h, shady? But the area is like 2 pi r squared h plus 2 pi, shady? When you are just doing this physics, just differentiate volume, always differentiate volume to get the area. Whatever volume differentiation give you, that's the area you are using for this. So if I've noted this, watch. This thing now, I told you that whenever the medium is a vacuum, K is equals to this. But if, for example, they give me that electric constant, K will be equal to 1 over 4 pi ER. Do you still remember? I said it. So if you know this, this is the one we are using because we are taking vacuum to be abundant. It is the most abundant surface. It has no interaction. When we say vacuum or air is abundant, we mean that it has less interference. So the medium is just free. Like electric field that you are conducting there, whatever you are getting should be enough for you to say, okay, this is good to go. So if I have this, let me replace K that is here with this thing. Remember that K is also given by 9 times 10 raised to power 9. Do you still remember? Yes. But we are not using this one because if we solve this, we should get this. So this is what we are using. Replace K that is here with this. So that electric flux will be equal to 1 over 4 pi epsilon naught, which is the temperature of free space, then times Q times 4 pi. Should be 4 pi will cancel 4 pi. Is it not true? So that you now have this thing to be simply Q over E naught. Is it not true? Exactly. So it simply means that electric flux is equals to EA, and electric flux is also equals to charge all over E naught. And the charge you have here, you can now come and put enclosed. The charge you have here, you can now come and put enclosed. Now somebody wants to ask me, how is he enclosed? Listen, do you remember that this is the charge that creates the field?
Yes.
Shebi? So it is the one that starts the whole thing. So it is enclosed. The test charge leaving or coming out, that one leaving or coming out. You are not seeing any of these things, so that's why Gauss law is there. But that particular charge that started it, you take it to be an enclosed charge. You can't see it. The one that creates the field, you never see it. And it's because you cannot see it. That's why Gauss now said, okay, since we can't see it, but what comes out as an output, we can feel it. We can actually say this is what comes out as an output. That means let's give a lot to it. So that is why we put this as always charge enclosed. Or you say source charge. It will always be the source charge. So Gauss theorem is simply these two things. Once you put these two things together, that's Gauss theorem we are stating. Once you remember, what we are having here is electric flux is equals to EA. A case can come, electric flux will be equals to Q over E naught. You can use any of these to calculate electric flux. But when it has to do with Gauss theorem, whatever you state, you must always represent it mathematically to represent this. Gauss theorem is simply EA equals to Q over E naught enclosed. This is what is Gauss theorem, this thing that you see here. So we'll define Gauss theorem now. So you don't come and say, we know that this thing is electric flux. This one is also electric flux because what is here is equals to this. But if they now ask you Gauss theorem, state it. Once you finish stating, mathematically, this is what you are supposed to give them. Or Gauss law, this is what you are supposed to give them as a mathematical representation for it. So source charge of charge enclosed all over permittivity of free space equals to electric field and area. This area, remember, there can now be different types of spaces. In our Monday class, what I will teach you in Monday class is going to be all about charge distribution. When it is a line of charge, what do you do? When it is a sphere, what do you do? When it is a cylinder, what do you do? When it is uniform infinitesimal charge, like the charge is going up and coming down, what do you do? So that will be our part of our class on Monday. That is charge distribution. So you can add this to it. Charge distribution. So please, to state Gauss theorem, you can now write Gauss theorem. So we are done with electric flux. Okay. Before Gauss theorem, I want to point out something. Can I get it? A question can come, they ask you, when is electric flux maximum? They can ask you a question, electric flux, which we know that it is EA, Sherry. Is it not true? We know that electric flux is EA. Electric flux is also Q over E naught. Is it not true? Individually. The minute you equate these two, what you are talking about is Gauss theorem. A question can come, they ask you, when is electric flux maximum? When is electric flux minimum? When is electric flux at an angle? So you can note it. Max electric flux, minimum electric flux at an angle. So we need to know all these things so that when you see questions or textbooks doing anything they are doing, they cannot confuse you. So we say that electric field flux is maximum when theta, electric field is maximum when theta, okay, am I too fast? Electric field flux is maximum when theta equals to 0. Electric field flux is maximum when theta equals to 0. Electric field flux is minimum when theta equals to 90 degrees. And electric field flux is at an angle when the angle is made with the normal and not the plane itself. I said electric field flux is maximum when theta equals to 0. Electric field flux is minimum when theta equals to 90. And electric flux is at an angle when angle is made with the normal and not the plane surface. Maximum when theta equals 90. Minimum, when theta equals 0. Minimum when theta equals 90. At an angle when angle is made with normal, not the plane. Sometimes it's confusing, like, but once you know that your cosine, how to find cosine with your hand, it will be easy. So what it means is that in those three cases, EA, those three cases, EA is gotten by doing, that is, electric flux is gotten by doing EA cos theta. The three cases given to you is simply, that English there is simply a case where we are saying EA cos theta. So EA cos theta for maximum, it will be when EA is having cos 0. And cos 0 is what? 1, Shebi? EA times 1 is what? EA, right? So at this point, this is maximum. Now, a situation, I'll prove it to you grammatically. A situation where you are now having EA cos 90. Cos 90 is what? 0, Shebi? Now, EA times 0 is going to be what? So at minimum, electric flux is 0. Okay? Then, when it's at an angle, like let's say the angle given to you, they tell you that there's an electric flux there, and the electric flux is equals to 60, is at 60 degrees. In this case, what you must do first, whatever angle you are given, you must first of all, I will show you why it's like this. You must first of all go to 90 and do 90 minus 60 degrees. What do you have? 30 degrees. So what you're supposed to do is EA cos 30 degrees. So when it's at an angle, another thing I want you to write there is simply EA cos 90 minus whatever theta you are given. Whenever it's at an angle, notice you will always do EA cos 90 minus whatever angle you are given. Because the angle you are given is because of something. Now let's see the something. So I've been able to do this up to Gauss theorem, so I can clean this part of the board. You now have this. So the only one I need to explain is electric field potential. We'll start solving questions. So we don't have this for this again. Then we'll do Gauss theorem. I explain Gauss theorem, then we'll do potential, then start solving questions. Something is making noise. Is it fan? Alright. It might look plenty, but it's not plenty. So this is like when the surface is flat. Let it not confuse you. If it goes this way, all you just need to do is to know that 90 degrees this way. So my normal will be constant 90 degrees. Okay, then now let's say okay, so see let's check something. Notice, why I said that first time, let's wait till we get here, is that there are 3 cases. And in my explaining, I was using like just one case. So that one case, if you are not doing the 3 at the same time, somebody will be finding it hard to pick because something is still remaining. So let's do the 3 together now, so you'll be able to pick everything up. Watch, this is a case 1. In this case, the electric field is moving straight down. Let's say, for example, I have charges on this now, flowing like an infinitesimal surface, flowing from up, is going up, and is also coming down. Charges are moving this way and moving this way. But what matters is that it's going through. So when it's going through, when it's moving along, and when it is at an angle. So notice, when it's moving through, and I think because of the fact that I was mixing it up, I was almost confusing us. See, when it's moving through, notice that the normal here is at 90 degrees. Is it true? Now, the electric field is moving this way as well. Also 90 degrees to this surface. Is it not true? Watch. But notice something. This normal now and the electric field, do they have any angle in common? Nothing. Like they don't make an angle, 2 of them. This is at 90, this is also at 90. Is it not true? Which means that the angle between electric field and normal here is 0. You get the point now? So in this case, when it's through, we say that EA is having cos 0 because there's no angle between the 2, and cos 0 is 1. EA is maximum. EA is maximum here. So you can say that when the normal, that's what I should have said, when the normal and the electric field are having the same angle, that is 90 degrees, 90 degrees, that means that your EA is maximum. When your normal and electric field is having the same angle, which is the same thing as saying they don't have any angle or any angle of intersection between them, your electric flux is maximum. But the second case now, which is along here, notice that if this is your N, normal force, and you know that electric field, you will not come and say, why don't you just limit to one movement? Why don't it be? No. Even us as human beings, we know that we can move up, we can come down, we can go left, we can go right. So we must consider different cases. So if your normal will always be determined, this fixed, it will always be determined 90 degrees to that surface, up or going down, depending on the direction or the position of that surface. So if the normal is this way and the electric field is going along, if it's going along, in this case, your electric field automatically makes 90 degrees. Makes 90 degrees with the normal. The minute it makes 90 degrees with the normal, in that case, your electric flux is going to be 0. Because in this case, what you're not going to be having is EA cos 90 degrees. That's the angle between them. And cos 90 degrees is 0. So 0 times EA is what? So in this case, we say that electric flux is minimum. But notice that in this case, they have no angle between them. So it's EA cos 0. And cos 0 is 1. EA times 1 is EA. At this point, maximum. important to note. Now notice in the third case, which is the last one, if you remember in first semester I told you, anytime you are doing physics, you're always going to be having the y-axis, x-axis, and when it's on a slope or at an angle. So if this be the case, whenever you are giving your electric field, you can only have an angle made between them. You can only have an angle made between them when they are having a situation whereby your electric field is moving along, your normal is moving this way. But the problem now is that it is not this particular electric field. Now, the electric field now that you are having here is a region. And this region, they are suggesting to you that something is happening at that region at 60 degrees or at any angle. So in that case, you will not come and consider that the normal and the electric field make direct contacts. What you now be considering is the angle they have and the electric field remaining. That is the angle that is made with that your normal, and the electric field remaining. So in that case, what you now come and say is, okay, total angle between this normal and the electric field is 90. So if it is 90, which means that actually what is happening is not that normal and the electric field is at 90 degrees. Rather, what is happening is that there is a charge or there is movement of your electric field at an angle to this electric field itself. So that is why we said you come and check that 90 and then do 90 minus whatever you are given, which is 60 degrees. If it's not always 60, it can be any angle. But once you subtract it, whatever you have is the angle you're using. Very important. You might want to mix it up because we've already told you that along means 90, but it's not that these two are in contact. Look at what they are talking about here. And this thing they are talking about, how does it relate to your electric field? Once you get it, that's what you are using. So with that said, let's state Gauss' theory. Hope I'm not too fast. Well, copy. You said? Fast. Newton. Here you see, out of 300 and something students, 300 plus students, you're putting their class. Here you see what I was saying in first semester. Should you see first semester by this time people are standing? Second semester they are. Do you know why? Some persons will use Friday night and be pressing phone. They will not sleep early. That's why. Because if you check it, most of them that are not in class, it's just that they are tired. And believe me, in their mind, they will believe that we will still reteach this thing. Even if I have to reteach this, I won't do it the way I'm doing it now. That's one thing about life. If you miss a particular day, what you are getting another day is that day's school. So, every occasion, be present. That is why sometimes, there are sometimes when your body tells you don't go for something. But when you eventually go for that thing, you witness something that makes you feel like, but what if I listened to myself and I did not go? That means I would have missed this thing. When it's good though, but if it's one that your instinct tells you not to go, always obey your instincts. Very important. Never joke with your instincts. Like Master Toka one time when he was doing his NYSC in Port Harcourt, he entered motor. That time he used to go to company work. He was wearing suits. He was carrying bag. They felt he's having money, big money inside his bag. The other is just phone and handkerchief that fill the bag. So as he entered bus, his instinct told him, calm down. But him, man, I'm believing that every day is the same. If it's my father, he will say, in his mind, he believed nothing will happen. Then I told him, give me that bag where you go. Hausa people in Port Harcourt, I'm telling you. As they said, he was like looking at them with like, what do you mean? They brought out dagger. Real life. They brought out dagger. They collected bag. Like motor was still moving though, they pushed him out of the motor. Real life. Master Talk, I happened to Master Talk, I'm telling you, real life. So why am I saying this? Actually, he obeyed his instinct when they picked one person. When he entered, he said that they picked one person. And he was not checking in his mind. He was not saying, his instinct told him. Yes, he said his instinct. He said his instinct told him, calm down. One man now told him to continue moving. He did not even reach small distance. they now told him, bring that bag with you. As he refused, they brought dagger, collected his bag, collected the phone he was using at that point, pushed him out. Now what I'm asking is, what if that pushing out, he now died, God forbid, or injured fatally? So please, always obey your instincts. Sometimes you go to somebody's house, your mind will tell you, at this point, start going home. One mind will tell you, no, let me wait small. They will soon bring lights. They will soon bring lights. Before you know it, you come and read online, they post, one girl did, one boy did, comment section will now full. So please, I'm telling you for fact, always listen to your instinct. And you're right, Gauss theory. Or you say Gauss law. Especially as students, don't joke with your instinct. Once he tell you, say you don't see him. Say you don't see him. That's why you did not witness it. It's better like that. You will not witness it, and then you come and tell me that that's why you now waited to see it. No. Gauss theory. Or you say Gauss law. The law states that the electric field flux, the law says that the electric field flux through an enclosed, let's do it this way, through an enclosed system, the electric field flux through an enclosed system is proportional. We said directly, I don't want to use directly because there's no such thing as proving it at the end of it. So it's proportional, it's just telling you what is happening. It's proportional to the charge coming out of the system, or charge, sorry, enclosed, because it's already filled. It's proportional to the charge enclosed, or you say charge in the system. Well, charge enclosed, but let me use in the system, since I'm using an enclosed system, it's proportional to the charge enclosed in the system. Don't go and say by the system. Everything I like English, no. We are saying something that is there. Yes. So, electric field flux. That means it's saying that both the electric field or the intensity and everything, that what is coming out is equal to what is inside. Because you cannot see what is inside. How do you see what is inside? By what is coming out. That is what his law is saying. How do I know that this amount of electric field is inside? How do I know that this amount of electric field intensity is inside? How do I know that this amount of charge is inside? It's by what is coming out. That is what his law is all about. So if you want to now put it mathematically, it's the same thing as saying EA equals to Q over E naught. And there are cases where if you come sometimes, they tell you to prove many things. They'll be telling you prove this, prove that. So their case is where they ask you to prove using Gauss theorem. They can ask you prove using Gauss theorem that electric field is equals to kq over r squared. This is how you go about it. The minute you find out that Gauss theorem, you are taking it in this case that Gauss theorem is simply EA equals to Q over E naught. We know that we use this to get this, Shebi. But Gauss theorem is simply telling you left hand side equals to EA. Right hand side equals to, that is telling you electric flux equals to electric flux. That is what you have here. Because this is what gave me this. Now in this case, if I come and replace the A here, the area here to be spherical. That is area of a sphere. By the time you put it down, you get this. 4 pi r squared E naught. Now if you remember that K is equals to 1 over 4 pi E naught. If you bring it, then bring the Q, bring the r squared out. If you check it, you see that it is not giving you electric field intensity. Are you seeing it? Because what you end up getting here, this thing, is that formula we got for electric field intensity. So any case where they tell you using Gauss theory, we will still need questions like that by Monday. Question 11 in your textbook, you see questions like that. So when they ask you using Gauss theory, prove that electric field or electric field intensity is equal to kq over r squared. This is what they expect from you. So with that said, let's talk about electric field potential. Then we'll answer those questions I gave you. If it's not fair, that is why I said we'll be doing charge distribution. If it's not fair and it's a cylinder, you're not going to be using 2 pi r L. If it's a line or maybe of opposite charges, this will just remain A. So it's part of what we're doing under charge distribution. That one is coming. But under Gauss theory, what he's using is just for spherical. And you know that charges move, even without thinking about Gauss theory. Charges normally, we say that charges move as a sphere in curved parts. And that curved part is as a sphere. So that is why we are using this. So what we are doing here is more like using point charge. Point charges move as a sphere. So when we now start doing charge distribution, that's where we'll now be making use of when it moves not just as a sphere, but maybe in a surface that is cylindrical or as a line. So that's what we do under charge distribution. So right, electric field potential. Electric field potential. We say that electric field potential is the work done. Anytime you see me say charge, I'm talking about what? Positive. So it is the work done in moving a charge, or you can say moving a unit positive charge. Sometimes people tell you a unit positive charge, but that's because they want to believe you don't know that charge talks about positive. If it's electron, I will tell you it's electron. So it is the work done in moving a charge, or you say a unit positive charge, from infinity. I don't like putting all these things about defining your textbook code or not defining our simple code. It is the work done in moving a unit positive charge from infinity to another point in an electric field. Work done in moving a unit positive charge from infinity to another point in an electric field. Why I don't like putting all these things is because first of all, where that charge is, you don't know it. Where it's coming from, you don't know it. So they are just trying to explain things for you well. But some people don't remember it. Some students won't remember it, it will confuse them. So you can just say that electric field potential is the work done in moving a charge from one point to the other. Finish. The work done in moving a charge from one point to the other. Finish. So all those other things they are putting there is to explain it for you. But it makes it somehow for some people. Work done in moving a charge from one point to the other. Finish. So if you like, let it be electric field. Where else will it happen is inside the electric field now. Because something will be created. Once something is created, that region is called electric field. So electric field potential is represented with V. If you remember in first semester when we did vector analysis, where I will come and tell you when this electric potential, I will tell you that you will now have minus V like this, then you will now have something like this. This so please, we will get there. That's not a formula. So that we don't enter the formula. See, I have V equals to work done in moving a unit charge. First of all, this is the first formula I want you to note. That's the first formula I want you to note. Then you need to remember that work done is given as S, should be?
Yes.
But in electric field, since it's spherical, whenever something is moving in circular paths, S changes to R. So that means that this should be FR all over Q. Is it true? Yes. And notice something. If you notice, when we did, so this is the second formula form, this is the first one, the second one. Now the third one is, if you remember, what did we say is force per unit charge?